All right, so I guess this is linkage and mapping part 3. But what I'm going to show you here mainly is how to apply chi-square to a sort of a linkage and mapping problem. And so this is figure 7.10, and it's applying the chi-square method to this idea of linkage or non-linkage. So what we have here is a test cross. So this is a mapping cross. It's just a test cross. So these are heterozygous for 2 genes. Y plus is brown, Y is yellow, CV plus is straight wings, CV is curved wings. And so we've got a dihybrid, heterozygous for both genes. We've got a homozygous recessive for both genes here in a test cross. And then we get the 4 things out of this. And the question, and then we count them up. And just keep in mind that if there's independent assortment, and this is a dihybrid test cross, we expect 1 to 1 to 1 to 1. We don't see that. We see 63, 28, 33, 77. Now, I don't have to do a chi-square to tell you that that's not a 1 to 1 to 1 to 1 ratio, but it's a good example, or it's a good opportunity to go through chi-square and apply it to this kind of a thing. So we can do that. So I'm not going to do this part, this contingency table thing. Honest with you, I don't really get what's going on there. You should probably review that. But I'll just do the normal chi-square thing. So the normal chi-square thing is, this just makes life more complicated. But so the way you do chi-square is I'm gonna switch over and do this on a Excel spreadsheet to keep the math easy. And I recommend that you do the same thing whenever you try to do chi-square. Get bigger. I think it's so small. And so just remember these numbers, and we'll go do it on. The way chi-square works, so the I guess we'll just say the chi-squared formula is O minus E squared, so that means squared, divided by E. So that gives you what we call the chi-square statistic. O minus E squared over E. So O is the observed number. So whenever you do a chi-square experiment, you're going to get some observed numbers. And so those are always easy. You just take what you observe and you put them in the observed column. Normally we just write all this stuff out, and I usually actually don't have students do all the calculations on a test because it takes too long. But we need that. So these are our observed, and we need to total them up. So our total is 201 in this case. And then we need the expected. So now the expected in this case, because the hypothesis we're testing, so our hypothesis is a 1 to 1 to 1 ratio. So 0.25 to 0.25 to 0.25 to 0.5. So now if we were testing a 9 to 3 to 3 to 1 hypothesis for a dihybrid cross, our hypothesis would be 9/16, 3/16, 3/16, 1/16. In this case, we're testing 1 to 1 to 1 to 1. So our expected is, if this is a 1 to 1 to 1 to 1 ratio, and we count 201 flies, I guess life would have been easier if it was 200 flies or cockroaches, I guess, whatever these things are. It would be easier. But so what you do is you take your total, and then you multiply that total So the way I got this, so here, I'll take this out of here. So this is, we're going to take our observed. So if you don't know how to use Excel, by saying equals D7, oops, equals D7. So that's going to be whatever's in this cell times, I guess we could make it B7 here. Oh, I did the wrong thing. So we want to always take the total. So we're going to take the total and say equals the total. And I could just multiply that by 0.25, but I'm going to multiply it by that and say, because if this was like a different fraction here, like 9/16, 3/16, 3/16, 1/16, then what I want to do is multiply this total by each fraction in each case. They're all going to be the same in this case because we're doing 1 to 1 to 1 to 1. Now that I've done this, if you look up here, I've got 201 in the formula bar times B7, which is 0.27. And then if I grab this little corner of this box and drag it down here, it fills all of these things in. In this case, they're all the same number. But if you look up here, it's 201 times B8, 201 times B9, 201 times B10. So if these numbers were different, then these things would be multiplied by different things. So it's super useful. Then we do O minus E. So here D7 minus E7, and then D8 minus E8, etc. And we get these numbers. And so this is chi-squared. So this is the O minus E part over here. And really what chi-square is measuring is the difference between what we observed and what we expect. And we just want to know if that's a really big difference, then we want to reject our hypothesis. So our hypothesis in this case is our data fit a 1 to 1 to 1 to 1 ratio. And we're testing that out. If it was 1 to 1 to 1 to 1, we expect this. And this is different than that, right? It's always going to be different because it's an experiment. But how different is it? So that's what we're trying to measure. How different is it? If it's really different, then we reject our hypothesis. So we get these O minus E numbers, but some of them are negative and some of them are positive. Because this is really, we actually have to put in I don't think I can easily put a sigma sign in there, so we'll just say sum. So that's, so each of these numbers over here is going to be a chi-square value, and then we add them up. So we need to add up all our chi-square values. If we added up these numbers with some positive numbers and some negative numbers, those negatives are going to sort of cancel out the positives, and it won't be an accurate measure of the difference between them. So that's why we square it. So in statistics, you want to get rid of negative signs a lot, and a common way to do it is squaring it. You can also do like absolute value, and there's some, I'm sure, complicated math reason why you would rather do squares, so they do a square. And then you take that square of these things and you divide it by the expected in each case. And again, in this case, the expected is the same in each case. Did that change? So all of these expected values are the same. And we get this. So this is our chi-square value. And usually chi-square values are pretty small. If we're going to accept our hypothesis, the chi-square values are like 1.2 or something. So this is a big chi-square value. But what we really need is a p-value. So we want to know what's the probability that this difference is due to chance. So if these numbers are close enough to these numbers, and there's just a little bit of difference, we could say, well, those numbers are just due to chance. We just counted up these cockroaches, and we didn't get, we're not going to get 50.25 cockroaches of each category. So there's going to be some difference just by experimental variation. But we want to know, is this a significantly big difference? So significant that we can reject this hypothesis. And so the bigger this number is, the more likely we are to reject the hypothesis. But we don't use this number directly because this number depends on various things and we have to come up with a p-value. So one thing it depends on is the degrees of freedom. And so the degrees of freedom are always the number of categories minus 1. So there's always, in this cross, there's 4 categories. So degrees of freedom is 3. So we have a chi-square value of 33.3. We'll round it up. And we have a degrees of freedom of 3. So now we need a chi-square table to come up with a p-value. And statology is the one I like. I can always tell because it's kind of blue and white. So you can go to this site, statology.org, how to read chi-square distribution table, and it'll tell you how to do it. It tells you what the distribution is, blah, blah, blah. And you can use the alpha level is, so the degrees of freedom we just said was 3. The alpha level is the p-value that we're going to use as our cutoff for what's a significant difference and what's an insignificant difference. And we'll just use 0.05. That's typically what we use. All right, so we're going to go down here. And down here are our degrees of freedom. So we got 3. So we're going to be looking at this row. The numbers in this row are the chi-square values that are calculated. Up here are the p-values. So it's kind of confusing because this df is these guys here and this p-value is these guys up here. And a really low p-value means to reject your hypothesis. So our hypothesis is 1 to 1 to 1 to 1. And we're saying, is this a 1 to 1 to 1 to 1 ratio? If our p-value is less than 0.05, then we're going to reject the hypothesis. So it's always a low p-value, you reject your null hypothesis. So because the null hypothesis means that your observed and your expected are the same, that there's no significant difference between them. That's the null hypothesis. And so are we going to accept that null hypothesis or are we going to reject it? And so here we're going to look down here. Our chi-square value are these numbers down here in blue and white. And it's getting really, really huge. So our p-value is way down here somewhere, over down here to where we want to build ourselves a ranch Sammy or do whatever these guys are doing. What are they doing? Oh, they're getting some Father's Day presents. So anyway, so our p-value is down here in the Hidden Valley. And that means our p-value, so that's our chi-square value, our p-value is super, 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 super low. So that means that we're going to reject this hypothesis for sure. But another way to think of these p-values, a couple things. One is this is the probability that the difference we saw is due to chance. So a really low chi-square value is a really low p or really high p-value. This means that there's a 99.5% chance that our difference is due to chance or just due to randomness. This is a 20% chance that the difference we see is due to just random fluctuation, a 10% chance, a 5% chance. And so just statistically speaking, we say if there's more than a 5% chance that it's due to just randomness, well, then the difference we see could be insignificant. But if the probability of that difference is due to randomness is low, that means it's probably due to something else. And so this is the probability that the difference between our observed and our expected is just due to chance. This is the probability of that. And this is 0.1%, so that's really low. Ours is going to be like 0. Like if we did a chi-square calculator, our p-value would come out to be 0. And so that would mean 0% probability that the difference is due to chance. Well, let's do a calculator. I like these little calculators. see if we get a simple. We have to put in all the data here. I don't want to put. Well, I guess we could. Yeah, I'd have to. Let's see. We could put in 3. Oh, we'll just say 50. Digits. Here's our chi-square value with 3 degrees of freedom, which is what we came up with. Our p-value is less than 0.00001. That is super low. Okay, so I think that's all I wanted to say about chi-square. This makes the math easy. It shows you a little bit of Excel stuff. Okay, so in our last video, we did chi-square. And I'm actually going to try to merge this onto that one, so we'll see what happens. So pull up our little calculations for chi-square. Because I forgot to really point out the big conclusion to this. So our p-value was less than 0.0001. So that means we reject our 1 to 1 to 1 to 1 hypothesis. If we reject that hypothesis, that means that the genes are linked. Because that means the hypothesis is, what do we expect if there's independent assortment? This is telling us that there's not independent assortment, and that means in this case that the